right, we're going to look at free body diagrams and forces today. This was lesson 2 in your notebook and your workbook. It may be a bit of a review from our last class, but I figured I'd go through the whole thing for you, so bear with me. So Fg is the force of gravity. It is directly south of any object, so regardless of any inclined planes is what I wanted to note. We'll look at those a little bit later. It's calculating using the Fg equals mg. Fn is the normal force. It's the reactionary force from gravity. It's at a 90-degree angle with the plane of the object, and it's usually balanced with gravity, and it is balanced with gravity when it's on a horizontal plane. So we can say that the force of gravity is equal to the normal force here. Okay, it's in absolute values because we know that they're equal and opposite, so they would have opposite signs. We're just looking at their magnitude in this one. So there's a couple things to note. There was 3. I took out the first one because it just talks about feeling the normal force pushing up on you on a chair. That's at the bottom of page 8. Don't confuse the normal force with the concept of net force. Net force is not the same as the normal force. The net force is where we kind of add up the vectors of force in equal and opposite directions. Okay, so F net comes from like an unbalanced direction. Fn is always there. All right, the magnitude of Fn equals the magnitude of Fg. Again, remembering that they're equal in opposite direction. We're just looking at their numerical value. Only for horizontal surfaces. Okay, so what that's saying is Fn and Fg are equal when this object is on a horizontal plane. When it's on an angle, all right, so some angle theta, we have our object sitting here. The normal force is 90 degrees to that plane. That's what I kind of spoke of on the last slide, sorry. And Fg is always directly south. All right, so they aren't actually opposite in direction right now. We talk about it in just a moment, but I would have to solve this for components. So Fy of g and Fx of g is what I would have to solve for to be able to add the two in the exact same plane here. Okay, so Fn and Fg are equal when they are on a horizontal surface. When they're on an inclined plane here, we have to be cautious of saying that. All right, the applied force indicates a push or a pull on an object. It can be horizontal, vertical, at an angle. Again, we would reduce that to its components. That's depicted on the top of page 9. So on our object, we can have Fa pushing, we could have Fa as like a pull, or again, perhaps we could apply this at some angle, and again, we'd have to reduce it to the components in the X and the Y. Okay, the friction force is any sort of stickiness between objects. It could also be air resistance. Friction is always in opposition to the motion of the object. Okay, so if something is standing still, we know that the applied force is equal to the friction force. All right, when they're unbalanced, that's when we can consider F net. So maybe our applied force is really great. F net would be Fa, in this case, take away the force of friction because they're opposite directions. All right, so again, we're looking at vectors here. So this comes back full circle to our last unit. All right, free body diagrams. Now there's one thing on this page, page 9, where it goes ahead and talks about F net. So we're going to look at that, and I'm going to get you to cross some things out and maybe kind of look at what I'm talking about here. So a free body diagram indicates all of the forces acting on an object regardless of their cause or directions. So we do not include velocity, displacement, or acceleration in our free body diagram. A free body diagram is forces only. Okay, my writing's not perfect because I'm writing on my iPad with a stylus, so bear with me. The net force is a sum of forces, and I've added in the direction where forces are unbalanced. Okay, net force on our notes, it says F net equals Fn plus Fg plus Fa plus the force of friction. We want to be careful because these are vectors. Remember, oftentimes they're all going to be in different directions. So we have Fn and Fg in the same plane. So I could add those, no problem, equal, opposite. And then we also have Fa, an applied force, and friction holding us back. Okay, so F net, in this case, if these two are equal and opposite, their F net is 0. So we don't add them in our equation, we kind of leave them out. We think they're balanced. Okay, F net in this case would just be the ones that are unbalanced, the arrows that are not identical, I guess. So in our case, we would just be looking in the horizontal direction to look at F net. Again, it's where they're unbalanced. Now, again, later on, we're going to look at a few things. So we can add forces that we call collinear. Remember vectors like this. We can add vectors like this. Sorry, we need an arrow there. But we can also have vectors that create a triangle, sorry. So we can deconstruct these to f of y and f of x and add those together to get F net, which has an angle. Okay. Note that since forces are vectors, the direction of the forces must always be included in our calculations. So up, down, left, right, north, south, east, west, or an angle if we end up with an angle. All right, we're going to get into a bunch of examples here. Feel free to skip ahead if you're like, I'm good with this one, or we did it in class. So a free body diagram for a car accelerating from rest along a level street. Assuming that there is friction involved, write an expression for the net force. So we start with a circle or a dot. That's where our free body diagram object is. We know we have F of n, and I'm going to try and make F of g look the same because they're balanced. The object isn't moving up or down. We always have friction. And if the object is moving, we know that the applied force has to be greater than friction. Remember, if they're equal and opposite, the object isn't actually moving. So we have an applied force in one direction. It doesn't say which direction, so we usually just apply it this way. Moving right across our page, doesn't really matter how you've drawn it. Remember, F of n and F of g are balanced. So the F net in the y direction, so F net in the y is 0. We don't consider it, okay? So I'm writing it here, but typically you don't have to. What we're looking at is the horizontal direction. We say that F net is equal to F of A, and we can say plus force of friction, knowing that we're going to give it a negative because force of friction is in the opposite direction, or the left direction, or the west direction. Or you can also say F net is equal to F of A, take away F of friction, because we know it has to be a negative vector. Okay? Whatever you'd like there, I'm okay with either statements at this rate. All right, a car being driven on a road experiences several forces. The force of friction due to the road in the air, the force of the engine driving the car forward. Describe what happens in the following situations. So because we're talking forces, we start with a free body diagram. Every free body diagram has F of n and F of g. Gravity affects us all. Okay, but we're not pulled into the earth, so there's always F of n. It's talking about a force applied. It should be larger than the force of friction at this rate. Just in this question, it does say the force of the engine driving the car forward, knowing that it must have overcome friction. we're going to look at a few different factors here. If the engine force, so F of A, is greater than the frictional force, what happens? Well, F net will be in a positive direction, all right, because we're moving forward in the right direction. And if that's the case, the car moves. Car accelerates. Okay, because remember, a force is equal to the mass times the acceleration. So if we have a force, this mass is undergoing acceleration. If the engine force is less than the frictional force, so let's say F of A is very small and the friction force is large, what's going to happen? Well, technically, F net is negative, okay? So, because the force or the vector in the east or the left-hand direction is larger, it will actually accelerate. But in which direction? In the negative direction. I guess I should have added it in our first example here. The car accelerates in the positive direction. Okay, last one here. The engine force equals the friction force. So if these two vectors are equal and opposite, F net equals 0. Therefore, there's no net force and the car doesn't move. Sorry, I just got to move my pencils off my desk. They're rattling. All right, so again, we've looked through a different scenario. Fn and Fg didn't really come into play because they're equal and opposite. We're just looking at unbalanced forces between F of friction and the applied force. So for a 60 kilogram mass, if the frictional force is 40 newtons, what applied force is required to accelerate the object at 4 meters per second? Okay, so we start with a free body diagram each time. All right, we have our object. It has F of N and F of G. Note that these keep coming into play. They should look equal and opposite. They're not perfect on my screen here, but that's okay. Force applied, and again, we have a frictional force. Hopefully, the frictional force is smaller than the applied force so that we're actually moving here. Okay, listing our information. M equals 60 kilograms. The frictional force, so F of F equals 40 newtons. We're looking for FA, and we want to accelerate the object, so A equals 4 meters per second squared. Sorry, I'm just trying to leave myself some room underneath here. So we draw the free body diagram. Check, check. We've listed out our information. We're going to calculate the net force using Newton's second law. So F net equals the force of friction plus the force applied. Now, our force of friction is in a negative direction. Okay, so we need to add it as a negative. So, all right, F net is always our mass times its overall acceleration. This equals the negative force of friction, and F of A is a positive. Let's add our numbers in. So we have 60 kilograms times 4 meters per second squared is equal to negative 40 newtons plus the force applied. So multiplying, we get 240 newtons equals negative 40 newtons plus FA. F of A then, we move our negative 40 to the other side, and we're left with negative, we add the 2, we get positive 280 newtons. All right, and again, our answers are all listed here just for you guys who are looking for them if you had incomplete examples. All right, example 4 I made a little bit smaller because we're going to need a little bit more room here. 2 ice skaters, Jim, who's 60 kilograms, and Bob, who's 40 kilograms, are standing facing each other. When Jim pushes on Bob, Bob's acceleration is 2 meters per second east. assuming that the frictional forces are negligible, meaning that there is no force of friction to concern ourselves with here, so we won't include it in our free body diagram. What is Jim's acceleration? All right, so what we're going to do, we're going to draw some free body diagrams here. Okay, so we always have f of n and f of g. And I'm going to draw this as Jim. Okay. I'm also going to do the same for Bob. So Bob and Jim are both experiencing gravity. Remember, because they have different masses, technically they're experiencing different forces of gravity. And this is Bob, sorry. All right, when they push on one another, they experience an equal and opposite reactionary applied force. All right, so I'm going to say that this is FAJ and this is FAB, just to keep them straight because we're going to be using those. All right. We are going to calculate the net force on Bob. So net F net for B, Bob, is his mass times his acceleration. Now, Bob weighs 40 kilograms. Okay. Bob accelerates at 2 meters per second squared. So Bob's net force experienced is positive 80 newtons. Okay, and he's heading in an easterly direction. Okay, we know that for every force there's an equal and opposite reactionary force. Therefore, Jim's force, applied force, is equal to Bob's force. They're equal and opposite. Okay, so we're going to say that Jim's applied force, who's actually in a negative direction, is equal to Bob's applied force in a positive direction. So we know that Bob's applied force, or net force, was 80 newtons east. Therefore, we can see that Jim's applied force is negative 80 newtons. Therefore, he must be going 80 newtons west. Okay, that's the applied force on Bob. Okay, so for Jim, is equal to his applied force. Again, because there was no frictional force. So, F applied for Jim is equal to his mass. I don't know what happened there. Mass times his acceleration. And we knew that that was 80 newtons. So, negative 80 newtons is equal to his mass, which was 60 kilograms, times his acceleration. We're going to solve for acceleration, and we get that acceleration equals negative 1.3 meters per second squared. And so our negative 1.3 meters per second squared translates to 1.3 meters per second squared in a west direction. All right, this seems to be a problem that's a little bit more advanced, simply because we end up with an angle. So 2 kilogram object experiences a 15 Newton force pulling south, a 25 Newton force pulling west, and a 20 Newton force pulling at 30 degrees south of east. What is the acceleration experienced by the object? So start with your diagram. We have this object. It's experiencing 25 newtons pulling west, 15, oopsie, I guess I need to add a 5 in there, 15 newtons south. I'm just going to move that number. And then we have one pulling, just going to try and draw my little grid there, 30 degrees south of east, and it's pulling at 20 newtons. Okay, and that was 30 degrees. So we just need to solve this for its components, and then we can add up the F net. Okay, so I'm just going to redraw my little triangle here. So we have our 30-degree angle, and we have 20 newtons here, and we get these two vectors to form our triangle. All right, so we're going to call this, I don't know, vector A, and we're going to solve for the x direction and the y direction. So this will be 20 newtons times the sine of 30 degrees, and this one would be 20 newtons times the cos of 30 degrees, and we end up with 17.32 newtons in an east direction, and we end up with 10 newtons in a south direction. So we're going to add up all of our resultant forces. So we're going to add the resultant in the x direction. So we had 25 newtons in a west, that's negative 25. And 15 newtons south won't come into play because it's not in the x direction. The other one we're going to look at is this guy. So we're going to add 17.32 newtons. We end up with negative 7.68 newtons in the x direction. Okay, so meaning this would obviously be a west. We're also going to add up the y directions. We had our negative 15 or 15 newtons south, and then we subtracted another 10 newtons in our y direction here. So our total should be negative 25 newtons, so south again. We can add these two together. So we get 7.68 newtons and our 25 newtons. And we'll draw our resultant vector, which is our net force. Okay, this encompasses all of the forces in our diagram. Now, because we didn't have FG, Fn being balanced, we had to consider our x and our y directions. Okay, solving for this, we're just going to use our Pythagorean theorem. So F net squared equals 25 newtons squared. I'm going to run out of room, so I'm dropping my units. Plus 7.68 squared. We get that F net equals 26.15 newtons. All right. We can solve for our angle here too. Our angle theta, so tan of theta equals opposite, so 25 newtons all over 7.68 newtons. Theta equals 17.1 degrees. Okay, so we've got our net force. We are being asked for the acceleration though. So remember that F net equals the mass of the object times its acceleration. All right, we don't need to consider positives and negatives, again, because we already have our direction. So 26.15 newtons equals, our object is 2 kilograms, acceleration equals 13, and we're 2 sig figs, so 13 meters per second squared, and it is 17.1 degrees south of west for our final answer. Example 6, if a 130 Newton east force is applied for 2 seconds to a 50 kilogram mass at rest, what is the resulting displacement of this object? So we only have one force being considered. Okay, so 130 newtons. So that is our F net. F net equals the mass times acceleration. So we have 130 newtons is equal to our 50 kilogram object times its acceleration. If I find its acceleration, I have its time, its initial velocity, we should be able to find its displacement. So acceleration from here equals positive 2.6 meters per second squared. So I have acceleration, I also have time, I had V initial, and we're looking for displacement. For this, I think our best formula would be VIT plus 1/2 AT squared, because this will equal 0, and we've simplified our formula. So D equals 1/2 times 2.6 meters per second squared times our time, seconds, and square that. We should end up with positive 5.2 meters. Therefore, we've gone 5.2 meters east. Don't forget that this is displacement, not distance. It needed our direction. All right, another one that looks like it's going to take a little bit of room, so I've made our example a little bit smaller. We have a 15 kilogram object being pushed from rest for 5 seconds by a 60 Newton east force, and that it is allowed to continue moving. Okay, so once it's continuing moving, our forces are balanced. The object eventually comes to rest. Now, it'll come to rest because we must have friction affecting us. If the frictional force is 20 newtons, how far from its starting point does the object come to rest? Okay, free body diagram, first steps. So we always have Fn and Fg. So I'm going to put those back in. We have a 60 Newton east force. All right, and then we also had a 20 Newton frictional force. So that was FF, and our 60 was our F applied. All right, so let's get started. With this, again, Fn and Fg are balanced, so we don't include them. So what we're going to do is we're going to calculate the acceleration over the time that it was accelerating, so the force is applied, and then we're going to calculate the acceleration over the frictional force. So when there's no more force applied, it's only friction. When we have these accelerations, we can calculate the distance that it's accelerating over. So to get started, we're going to look at just that first piece of time where the object is accelerating, all right, or being pushed, or it has that applied force, however you want to think about it. So the first portion, we need to calculate an F net, because we have our 60 newtons in our positive direction, and we also had friction affecting us and holding us back. So we have an overall positive 40 newtons force. So we're moving with a force of 40 newtons in the east direction in this case. So with that, in our first period of time here, we can say that F net is equal to the mass times acceleration. We have 40 newtons, and our mass was 15 kilograms, and we're going to find acceleration. So acceleration is positive 2.67 meters per second squared here. Again, that's moving in an east direction. So we can find the displacement over that time. Now, we started to push this object when it was at rest, okay? And it started at rest, and we accelerated or pushed it for 5 seconds. So I'm going to, again, use VIT plus 1/2 AT squared. Because it started at rest, V initial is 0. And we get to say that distance equals 1/2 AT squared. So 1/2... acceleration was positive 2.67 meters per second squared. and time was 5 seconds squared. So the distance traveled was 33.375 meters while we were accelerating it. Okay, so that is the distance for the first piece. Sorry, just trying to carve out some space. Now, in our second piece, we know that F net, once it's moving, we no longer have an applied force. Okay, so our applied force is gone. F net will just equal the force of friction. Okay, because again, our normal force and gravity are still balanced. The only thing that's unbalanced is the fact that only we have friction. So F net then is equal to negative 20 newtons. All right, so mass times acceleration equals negative 20 newtons. Sorry, I'm just going to write that in for the sake of saving space. So remember, F net is mass times acceleration. So again, 15 kilograms times some acceleration, now we're decelerating hopefully, is equal to negative 20 newtons. Acceleration is negative 1.33 meters per second squared. Now, we don't know how long this is happening, so we can't use the same formula. What we can do is go back in time here, and we're going to use the information from our first piece, or our acceleration, and we can find the final velocity here. Okay, it accelerated for 5 seconds at a rate of 2.67 meters per second squared, from rest, so we can find final velocity. This will help us because we could use then Vf squared equals Vi squared plus 2AD. Remembering that our final velocity, if it's slowing down because of friction, will be 0. Our initial velocity, in this case, will have been the final velocity in our first piece of information. We have acceleration, we can find distance. Great, so let's do this. So I'm going to go back to our first piece where we were accelerating or pushing the book, and I'm going to use A equals Vf minus Vi over T, and I'm going to solve for Vf. All right, so 2.67 meters per second squared for 5 seconds, and Vi again was 0 here. All right, we started at rest. So we get 13.33 meters per second. It accelerated from 0 to 13.33, and now we're going to use that in our second piece here. So I'm going to solve for displacement, which will be Vf squared minus Vi squared all over 2A. Running out of room, so I'm just going to go up here. So Vf squared is 0 meters per second. All right, it comes to a stop in the end. Take away our initial velocity was our 13.33 meters per second. Once I stopped pushing it, that was its initial velocity. All over 2 times negative 1.33 meters per second squared. That was my acceleration or my deceleration from friction, and I get a distance of 66.8 meters. So it traveled 33.375 while we were pushing it. It took another 66.80 to slow down from friction. So the total, D total, is 33.375 plus our 66.80, and we get 100 meters. Okay, it is the distance, how far from its starting point does the object come to rest? 100 meters. I guess you could say it would be 100 meters east of where it started if we really needed a direction, but we don't. All right, last example. A force of 90 newtons is applied to a sled that has a mass of 40 kilograms at an angle of 30 degrees to the horizontal. If the frictional force is 27.94 newtons, what is the resulting acceleration of the sled? Okay. Diagram. Having a hard time. Okay. Sorry, these should be equal and opposite. Having a hard time with my stylus. Fn, Fg. We have a force of friction, and we know that to be 27.94 newtons. And we also have an applied force that is 30 degrees from our horizontal here. And that was 90 newtons. So we need to solve for components here. We end up with this triangle where we have 90 newtons as our hypotenuse. This is 30 degrees. So the applied force in the y direction will be 90 times the sine of 30, which is 45 newtons. We have the applied force in the x direction, which would be 90 newtons times cos of 30. And I got 77.94. All right. So, what we know is that this sled will be accelerating along the horizontal in the end. Okay, so its path will be horizontal. Therefore, tricky enough, we actually don't care about the y direction in this one. It's not being lifted up. Okay, so that is the tricky part here. We are going to look that F net is equal to the force of friction plus the applied force in the x direction. Okay, one more time. The object is not being lifted up. Its path is going to be horizontal in the end. We are going to only calculate the acceleration in the horizontal direction. Therefore, we are only considering the horizontal direction for F net. Okay, so force of friction is negative 27.94 newtons. And in the positive or x direction, we have 77.94 newtons. We get an applied force, or net force of 50 newtons. F net equals mass times acceleration. So we have 50 newtons is equal to its mass, 40 kilograms, times acceleration. Acceleration becomes 1.25 meters per second squared. I guess we should actually round this to 1.3 meters per second squared, and it will be accelerating in the east direction, or whatever direction. I guess I can't say east because it didn't actually mention that in the question. It's accelerating in a positive direction. All right, our homework is all odd questions from page 5 to 10 of the workbook. Now, I recognize that this is a lot. Free body diagrams, if you guys can do this, we're going to be set for the rest of the unit, okay? We just add a few different forces in, but we need to be able to know how to calculate F net and what we can do with it. All right, so you started this on Friday. Hopefully you'll have a little bit of time to work on this, and that a lot of this was review already in our lesson today. Get started, and I will check in with video tutorials as much as possible with you guys to give you a hand. All answers are all posted online, so you can always check your work there too if you need to.